So last time we were talking about some switch cap where we found out such setup. Phi 1 and phi 2 are non-overlapping clocks. Then this is equivalent to a resistor whose value is equal to C, right, or TC by C. So this can be done using simple switch cap circuit, but whenever you are adding switches and all these things, they like you are inviting lots of problems, right? One of the problem is called charge injection, which we already talked about it maybe last time. But before going to that, like charge injection or other things, there are some problems like noise. So I'll just touch this topic very quickly because it has to be part of analog. If I'm going to touch this, like it will take a longer time. Noise, you need to read it because there are two kinds of noise: thermal and flicker. So this is what I'm going to touch this, and then we'll quickly go to next topic, which is on switch capacitor circuit. So by the way, you got confirmation from Vijender that you have your assignment number 1 exam on Saturday, right? Okay. And comparator will be reviewed this Saturday, right? So Hindu will be reviewing your comparator design. How is the comparator design going on? It's done, or with the deadline now you can start maybe on Friday evening. Anyway, so generally, so there is a white noise. You must have heard about these things: white noise or the white spectrum of noise, color noise, right? You must have heard these terms maybe in probability or estimation of signals and systems. Such subjects deal with such things. So we are going to touch only few things and then we'll go to the next level. So this kind of noise for from minus infinity to plus infinity, you are having some noise, and this is the probability density function, which is always some line. This is white noise. If it is available at particular frequencies, it's called color noise, right? However, when you are doing this kind of thing, your circuit might be having some response, and when it's multiplied with the noise coming from maybe circuit or maybe from some component, in total at the output you are going to see this, which is multiplication of these two, right? Sometimes that system which I have drawn here, the system may be replaced by such band pass or low pass or high pass kind of system. So this is a band pass system which is having some, let's assume that it's some 100 hertz to 4 kilohertz of band pass, and if it is going through following things, if the input probability density function, if it is went through this telephone line, at the output you are going to see this, or if in time domain if you have such things, then at the output side you are going to have just 100 hertz to 4 kilohertz of frequency signals. You are not going to have anything else, right? It will be in between these this band of frequencies, right? Now sometimes you have seen two-sided or one-sided spectra, right? So whatever you have plus side, it's at negative side, same thing will be there. So we are interested generally in one side. If you are drawing this Bode plot or something, if it is like this, the negative side will be like this. This is already known to you, right? Such filter is known as brick wall filter. Right? So you have heard about all these things, right? There is no problem. Okay. Now, if you are at high frequency, just note that if you are at high frequency, you are going to observe a thermal noise in resistance, and it's going to be happen because the random motion of electrons in a conductor introduces fluctuations in voltage measured across the conductor, even if the average current is zero, because of thermal effect. So if you are observing some signal, let's say I am giving from a supply of, let's say, 1 volt power supply, which I am connecting here. I am not going to see 1 volt power supply, but 1 volt is an average value, but in reality you are going to see this, right? So this is high frequency noise, and this is happening because of the fact that there is a resistance, and that resistance has random motion of electrons, which introduces fluctuations in the voltage. So this is the standard definition. If you are seeing anywhere resistance, that is going to give you thermal noise for sure, right? And you cannot avoid it. And there is an approximation that it's going to be equal to 4 kTr when it's drawn SV of f, and it has been uh, observed, and it has been symbolized as Vn square and then one line on top of it. You can make this one also. If you are making Vn, you can make In also. There are many ways to note, symbolize, or you can write down its equivalence. The value of the unit of this one will be volt per root hertz. Current is ampere per root hertz. This one will be amp square per hertz, and this is volt square per hertz, right? This is noise in terms of voltage or noise in terms of current at a given frequency. If you are taking the integrated noise, is measured in terms of either voltage or in hertz, or in ampere. There is no hertz because it's integrated from some frequency to another frequency, so it's not with respect to some hertz, right? So it's a band of frequency. So generally SVF for resistance, noiseless resistance is not going to give you anything, but if it is random motion of electrons in a conductor, so this is probabilistic function, and this process is stochastic. However, we are actually making it to 4 kTr. So this is an approximation, and this is probability function, which is, so we are not going into the derivation of this thing. Okay. So you might have such circuit where there is a resistance and capacitance, and you might have VR square. You can see that even though there is no input, but there is a VR square, which is actually the noise signal which you are giving as an input. Then what is going to happen? This circuit is a low pass filter, which is already known to you. What is the transfer function? 1 by 1 plus RCS, right? So if you are taking the square of this multiplied by SR of f, which is actually the 4 kTr, that is going to give you S out of f, right? So you are going to see this thing, and you know what is the cutoff frequency, right? Other than that, we are more interested in the power. So when you want to take the power, same equation which we have found out just now, that you can integrate it from 0 to infinity 4 kTr divided by the transfer function for band of frequency, and using this formula you can have 2 kt by pi c times tan inverse u. U is from 0 to infinity. So the power, noise of the power at the output is equal to kt by c. This is an important actually important derivation. So power of such kind of noise, when it's RC, just a RC circuit, you are going to see kt by c. The power of that noise is equal to kt by c, right? So this is the reason why whenever there is a switch capacitor circuit or any circuit which is whose lump or distributed model is RC, the noise of that one will be kt by c if you are operating that one as at very high frequency. So you are going to see kt by c noise. So that's why at high frequency this such kind of noise is known as kt by c noise also, right? Just keep this one in your mind. If I want to have if I want to decrease such noise, what I need to do? What do you think? If this network is going to give me noise of 1 microvolt per root hertz, I want to reduce this, what I can do? Yeah. So increasing resistance will not help you at all, because the power of such system is equal to kt by c. It's depending on Boltzmann constant, T is temperature, and C is capacitance. So capacitance you can increase it, no problem. If you are increasing capacitance, you are going to have decrement in your noise, right? Yeah, Nishan.
So thermal noise is generated by the resistance.
Resistance.
But the power is dependent. Power is not dependent on resistance.
No. That is what going through this equation. It's following the equation. It's not about some physics. So physically, it has been proven by the mathematics that it's not depending on resistance. It's depending on capacitance. So that's what I'm giving you. The power equation is not. So there is no physics right now. There might be physics explanation also, but we are, like, as an engineer, we are going through mathematics. So mathematics says that it's kt by c only. Right? There are many places where you have been explained by equations. So this is also being explained by equation only. Right? Okay. One more noise which is known as flicker noise. This noise only happens at very low frequency. That's why this is known as 1 by f noise, because as f is increasing, this noise is smaller, but f is smaller, this noise is higher. So 1 by f noise is equal to flicker noise is happening at low frequency only, and this is happening because of the dangling bonds of the lattice structure of your silicon, where these charges are being trapped while the having those operations at very low frequency. Because by the way, I can ask you very quickly, so there are two kinds of MOSFETs, where I am applying here voltage and applying here voltage, right? I should have drawn actually the AC one. Here I'm applying. Okay, let's go to the second part first. So if I am applying here very low frequency, what will be the CGB versus VGB? So gate to body. How does it look like? Yeah, so all the people who have made SRAM, they should know this, right? Including you. Others also have done it. So tell me. Hmm? So you are saying constant in, okay, and then such. So this is actually accumulation. This is cutoff, weak inversion, strong inversion. Here you are going to see COX, CGB, again COX, right? That is how it goes. So this is for low frequency you are saying. What is going to happen if it is high frequency? Hmm? This, okay, but why is it like this? Why is it going down? Why not? You haven't seen strong inversion ever. If you are making this MOSFET, look, we always want a MOSFET which is going to see COX, right? So why this is going to happen? So what? Look, there is a strong field here, right? So if there are two dissimilar plates and frequency is enough to create a capacitor, I'm not talking about zero frequency.
So variation of the depletion rate that the frequency is not matched. That's why.
But there is, look here, it's a strong field. I'm giving strong field. It's ground. Do you understand? Capacitance, depleted capacitance, and those things. What do you mean by depleted capacitance? Means one side you have, higher potential, another side lower potential. Then at the surface you are going to have this exchange of this whole pair, and that is going to create a capacitance, right? Right. So same thing we are doing, no? So there has to be capacitor. There has to be capacitor because this thing is happening. So I'm not going into too much into detail, but you're going to have this one because there is a strong field which is relatively lower than what you have here. Look at this. However, if it is two terminal device, what you are saying is, or what you have studied in your BTech and what you are saying on the basis of that, it is for high, right? And this is for low. Please revisit two terminal MOSFET and three terminal MOSFET. Both are different thing. When you are doing this drain and source are open, right? So there is no field is available. That's why those charge is getting trapped and those are creating a capacitance. Here it's not happening, right? And I'm talking about the bigger technology node which are not deep submicron. I'm talking about even 1 micrometer. Of course, it is going to happen in 28 nanometer, but 1 micrometer when there is no overlap capacitances are there. Still, this is going to happen, right? This is what I wanted to explain you here. So at low frequency, those extra charges will be trapped. Can you see? It's only polysilicon, silicon dioxide, and silicon crystal. There is nothing like a drain and source right now. If that is the case, then and then they are trapping here. If, if it is not there, If it is not there, if I am connecting here drain and source which is grounded, it will be pulled out. You understand this? Yeah. So what I want to explain, when you are at low frequency and such kind of structure is available, you might be having a possibility to have extra charges trapped here in, this dangling bonds, right? In the latest structure you may have, this is irregular structure. Still I should not say that this is going to be look like this one. It might be just a picture which is going to be look like, it might be something different, it might be something like this also, depends. So this is an approximation. So if you are at low frequency, then you are going to observe some noise, and that noise is nothing but Vn square equal to K divided by Cox W times L times 1 by F. So look at this value. Is it familiar to you or no? What is this value? This is the capacitance created between this point and this point, right? But this is two terminal, by the way. It's, there is nothing, drain and source are not available. So this is equivalent capacitance. So there are two kinds of capacitance. Just let's revisit this. If there is a prime symbol, means it's per unit area. If it is not per unit area, you need to multiply with an area. So that is going to give you the total capacitance of your transistor, and that is going to be divided by some number K and multiply by 1 by F. That is going to tell you how much noise contribution is coming for a given capacitance, right? So it's low and high frequency will take care of this. So it's a flicker noise, right? So there are two things we are discussing. If you are at very low frequency, as low as Saswat, nowadays I call Saswat as low frequency, where he is working at sensors, right? And high frequency as high as, I don't have right now, maybe Dinesh is not here. Dinesh is okay. So as high as 1 GSPS. Right? So this is going to bother me when the frequency spectrum density will look like that way. So thermal might be Kt times R for a single resistance. However, at the lower frequency, you are going to see such kind of plot coming from the equation which we have written here. So it's some number K divided by Cox W times L multiplied. So these two are constants. Cox is the varying quantity which is coming from here, that has to be taken into account, multiplied by 1 by F, right? So that is what you are going to see. So it's on log scale, so do not get confused with, this is not a linearly decreasing, but this is exponentially decreasing, by the way, right? And when you are connecting both of them, you are going to see something called FC. We are going to call this one as flicker corner. So at this point, if you are working below this frequency, definitely this particular the noise amplitude is going to bother your circuit, right? So if you want to design something at microvolt, let's assume that. So let's take the example of what Saswat is doing, or Pratik and Raman are doing. So you are working at, what is your input frequency? 11 kilohertz, right? So you want to design something from 5 to 15 or 16 kilohertz, right? This is your range of frequency. Now what about amplitude?
48
Hmm?
48
No, in terms of voltage, can you tell me?
7 microvolts.
So 7 microvolt. at the output after his system, how much you are expecting. Let's say you are going to reach till 3.3 volt, that's the supply voltage, right? But when it's going through this circuit, which is non-linear by nature, by the way, and if I, even though I feed 7 microvolt at, let's assume that 11 kilohertz at the output, I am going to see, let's assume 3.3, but I am going to see 22 kilohertz, 33 kilohertz, 44 kilohertz, and so on, right? Because this is non-linear circuit, it's passing through this non-linear circuit, so you are going to have so many beams of the signals. So this is basically tell you what will be the signal to noise ratio. This floor is known as noise and this is known as signal. Sometimes all these power electronics people doesn't like to call SNR, but they deal with total harmonic distortion, which is also one derived function of this noise and fundamental, right? And harmonics. So if you are dealing in that, and if this extra noise, which is, even though you are keeping your system off, you are not giving anything, I don't give anything, I haven't given anything, still I am going to see some frequency components, right? That frequency component, if the amplitude of that one is higher than this one, let's say at 22 kilohertz, 33 kilohertz, some extra noise has been added by my system also when it's zero. That is what I was calling this flicker and thermal noise when the system is not on. On means, I should not say on, uh, even though there is supply voltage, but there is no input. If there is no input, still you are seeing some extra voltage which is going to be there, and once you are going to add the input, they are going to ride on top of your input, right? So this is not in your hand. If you want to reduce it, you need to reduce overall capacitance. For the case of KT by C noise, for flicker noise, right now you can't do anything. It's not so simple as KT by C, right? You need to use some different technique, right? So those techniques are like, you can use chopper stabilized amplifier, or you can use CDS. What is the full form of CDS? Correlated double sampling. So these are well-known techniques available in many books, right? So you can these two, right? So you can remove flicker noise or you can reduce it. However, if it is not into the range, so when I'm saying how much is your range means, if I want to see 7 microvolt as an input, if I know that, like this is in total is around, let's say 700 microvolt, and this is around at 3.3 volt. The distance between this fundamental to noise is going to give you SNR, and this SNR has to be defined from the required dynamic range of your circuit. So that is already defined. So from dynamic range you can find out how much is going to be your uh, required noise. So when you are simulating it, maybe you will have some value of noise you are seeing. So that noise has to be budgeted for a given range. That is how it has to be done. Right? So anything which you are bothering? Okay.
How to find that flicker problem.
Flicker. Okay. So this corner is generally when you are simulating the circuit, then you will get it. This is one thing. Yeah, and it depends on the value of capacitance also. So you cannot define that will be the value, but generally this is coming less than 1 kilohertz or maybe around 1 kilohertz. Above 1 kilohertz we are going to call it high frequency, or you are into thermal noise, right? So maybe like for his case this might be higher frequency node, and you will not see any.
What are those problems if we are working at the flicker zone? Means near to the flicker zone.
Near flicker will not be the much problem. Let's say you are at 2 fc, still okay, and you can manage it using value of capacitance and resistance, or you can increase or decrease value of transistor, and then you can look. You can see if you are increasing value of w and l, if you are increasing it, you might have lower flicker noise. Same as previously, like capacitance you are increasing, again you are increasing capacitance. This kind of noise, if you have a system which is noisy system, if this is output, if this is input, and gain is already known to you, so if you can find out the noise at the output, that noise is known as output noise. Because of this, when you are shutting off, there is no input, and if there is an input, right, accordingly you can find out what is the output noise. However, when you have if you want to find out output noise, there is something called input referred noise. So as we have found out from the equations, by keeping the equations for the whole circuit, you can have noise which is known as input referred noise. When you are multiplying this with input referred noise, you may have availability of the output noise. So same thing you can do it in cadence. So whatever noise you are actually measuring, it's input referred noise in the cadence. So if you want to have the output noise, you need to multiply with the gain plot, which you are doing in AC analysis already, right? Okay, let's come back to where we were, and we were at following things. If you are having such system, there is a switch cap, you might be operating this circuit as high frequency, at low frequency, accordingly you may have noise. That noise has to be rectified. So if you want to rectify it, capacitance needs to be increased in this case, right? If generally these circuits are applicable at very high frequency, switch capacitors are very high frequency, so you need to increase capacitor. However, when you are doing this, we already learned that there is a function generator. that there is a 50 ohm impedance and there is a capacitor. So when you are switching this off, there is an availability of extra charge in the channel. Half will go this side, half will go this side, because there is an approximation that this side also we are seeing 50 ohm. If it is not equal, it will be something different, right? So this was one thing we learned, and this kind of thing is called charge injection. One more thing is that if you are not doing this, but you are operating the whole circuit at very high frequency, where there is a capacitor and there is a clock going from 1 to 0, 0 to 1, right? If it is 1, no problem. 1 is not a problem. During 1, this is completely on, and you are going to transfer the voltage at the output. So this will be track and hold, right, as you are saying, right? So input will be tracked, but when it is off, in this phase, in off phase, what is going to happen? We are thinking that this is off, and right now we are not talking about charge injection. So even though there is a charge injection, there will be something else also. That else is, when there is off, still it's not completely off. You are, when you are going from 1 to 0, there will be some ramp down signal or maybe ramp up signal, which is not going to make this transistor completely off, at least at the transition. So that extra charge, when it's going from 1 to 0 or 0 to 1, that charge will be dumped here through a capacitor. Same thing is going to happen here also, but as previous circuit is a function generator connected to 50 ohm, no problem. But if it is connected to something else, this is a problem again. It will be again reverse side, you will observe such thing. This kind of phenomena is known as clock feed through. Right? So your clock is getting back to the node. Right? Now you might be looking at various things. Those things are thermal noise. If you are at very high frequency, if you are seeing somewhere resistance which is offered by a switch, so that resistance and capacitor is creating a noise range which is thermal noise, and its power will be kT by C. So you can reduce it by increasing C. There is one more thing, charge injection, and you might have clock feed through. So look at this, there is only single switch and capacitor is inviting these many problems. So when you are designing any switch capacitor circuit, we need to make sure that they have to be within your budget. So we need to make the budget. So I can tell you that, okay, if noise requirement is equal to 1 microvolt, thermal noise, I am telling you that it has to be less than 1 microvolt, then you can you design the value of capacitor? K and T are already known to you, right? KT by C has to be less than 1 microvolt. So you can find out the value of capacitor by putting K and T value, Boltzmann constant and temperature, right? So this is what you need to do, right? Now there is one more thing, how to reduce. So thermal noise, no problem, you can increase the value of capacitor, you can get you what you want. But if you want to remove charge injection or clock feed through. So before teaching this technique, which myself never use this, so I'm telling you this is a dangerous technique. If you are using it incorrectly, then you will have more noise. Okay, so that's why I generally don't use anything. And as an analog engineer, you need to understand only one thing: do not add extra transistors or do not remove something which is already well proven. If you are adding something, you are inviting so many problems. No, do not add anything which is new. But if you are 100% sure there is something new by adding that particular transistor, you will get some gain. Then you can add it and you can patent it also, right? So first of all, do not add anything, okay, until you are not sure what you are doing. If you can design something with the minimum number of transistor as low as one, that's the best one. It will not give you any noise, any problem, right? Do you want to see one amplifier which will be only with one transistor? Do you know about this? Hmm? Sorry,
That's GMR.
what do you mean by G1? Okay, so you are saying that one transistor like this, and only like this. What about load? How you are going to get this one?
There should be some.
A load, but if you are connecting load, then it's not one transistor. Okay, but you are right. This is also one way. But there is another way I'll tell you. But if you are expert of MOSFET, then and then you can understand this. Okay, so I'm drawing it by device. Okay, so if there is a V in, which looks like this one, and there is a clock which is going on at the back. Yes, Nishant, right? Are you following me, right? Okay. So when I switch this on, I assume that there is enough high voltage which is going to make the channel here strong inversion. So what I'm going to observe here, when it's on, input charge is equal to V in times value of capacitance. So how much is the value of capacitance? I'm going to see. Somebody told correct answer. C ox, right? Okay. When I'm writing C ox is equivalent to W times L times C ox. Okay. So okay. Now I am doing something that I'm going to connect this to a VDD by keeping this off. What is going to happen? Sandeep, what do you think? Hmm? Current? Where? Where? Look, I am seeing four terminals and I don't know what you are talking about.
From drain to source, no current.
Drain to source, no current. But why? We're talking about all these things. If I'm asking you, current is a, a philosophy where there is a conductor, right? Let's assume that this is a rod of metal. If I'm flame it, so there will be thermal bond which will be broken, hole will be created, and this hole will travel from here to here, exactly in the opposite direction. Electrons will be there, right? So hole will be sitting on some electron will go another side, right? So this will happen. So in the direction of hole or in the opposite direction of electron, you are going to observe a current. This is what I understand. So now tell me. So I can see current, by the way. If electron hole something is moving here and there, then something will happen. This is what I wanted to teach you last time also. So how this electron will travel, or so this is very high potential, which is like this, right? This is connected to VDD. If this is connected to VDD, what is going to happen? This guy is going to ask all these electrons to come out. It will pull out all the electrons, and as many number of electrons it's pulling here, same electrons needs to go at the negative side. Means those pulled out electrons will go to depleted. So effectively, what are you observing here? Capacitance reducing. So when I'm doing such going into such structure, I'm going to see this thing. And as Siddharth has told last time, threshold voltage is depending on one fact, that when you are adding plus and this side minus, after having one extra plus, you are going to have minus in the channel, and that is the starting of forming the channel where you are in weak inversion. When this entire bridge is created, it's complete channel, and you are going to have the Cox, or you are in the saturation mode, right? So if it is capacitance, let's say VGB versus cap CGB, this is the point where this forming of channel is happening, and this is the point where forming of channel is done, right? Between this point and this is a very narrow band. This is also known as sub threshold, by the way. At this point it's exactly threshold. This to this point is called sub threshold, right? And if this is happening where Cox is much higher than CGB, means if these two are the equations which are going to govern your circuit, means input charge is equal to Cox times V in, output charge is equal to CGB times V out. As we know that charge cannot be destroyed, cannot be created, so whatever we have, they have to be equal. When they are equal, V out by V in is equal to Cox by CGB. If you're following this, you can see that Cox by CGB is lower, so V out will be higher than V in. Yeah, this is called discrete time parametric amplifier. And the parameter is capacitor. This is 2007 patent which I am discussing. Right. So At the output, you are going to have the amplified version of what you have done, right? Using a single transistor. Right? So if you can do something like this, then it's a $1 billion job, right? You can have lots of things. So do not add something else. This is what I'm saying. Do not add so many things. If you can add only one thing, it's good. Or if you don't understand how to use it, do not use it. Okay. So I am not in like oppose of this technique, but I am not expert enough to use this technique. That means that. But if you are expert, you can do it, right? So what this technique says, the delta Q charge is going to be available at this positive plate of the capacitor, right? Now this is happening in from clock going from 1 to 0, but I'm adding one more MOSFET which is going from 0 to 1. When it's going from 0 to 1, this MOSFET is coming into strong inversion, or it is going to give you equivalent of Cox capacitance. If you want to find out the exact number, it's Cox times W times L, right? In reality, otherwise Cox prime is equal to per unit area. Whenever you are saying prime is equal to per unit area, there might be new like terminology for you, right? So Cox is nothing but epsilon A by D, but generally like this is epsilon by D. And that is what we are doing, and D is nothing but the thickness of the oxide. Thickness of the oxide is exactly this one. So this is metal SiO2, and this is called oxide area. I am talking about this thickness. So that Tox is going to give you Cox, and as you are increasing W and L geometrically and mathematically, you can prove that it's Cox times W by L, right? It's per unit area, and as you are increasing, those many capacitances or those many plates are coming in parallel, so W by L has to be multiplied, right? So whenever you are seeing such structure, it's equivalent to MOSFET. So there is a capacitor from here to here. If you are connecting it, it's going to give you equivalent capacitance of Cox, and this is not going to be only traveling here, the extra charge, but it will also travel here also, right? Because there is one more path, and you will pulled out all the charge which were going here. So delta Q1, if it is going here, delta Q2 has to go to another side. However, when you are doing it wrongly, means so you can see the charge distribution, how it is going on if you are using this. So that was an idea, that you are keeping some value of capacitor which is going to pull out delta Q1 into itself. Then you have the zero fluctuations. So when you are doing this, when it's going from 1 to 0 and this is going from 0 to 1, you can see that there is a capacitor which is this one, W1 times C overlap. So it's overlap capacitance. This is head capacitor, no problem. And this side, there has to be two capacitors. Can you see? Even it's not one path, but there are two paths in parallel. So it's 2W2 times COV. COV is equal to overlap capacitance. Right? You agree with this one, right? This model. So you have to make sure that whatever this W1 is there, if W2 is equal to half of W1, then this capacitor will be same. So that is the reason why you are doing it, you have to be careful, otherwise you will inviting some more problems, right? So if you are one more time when you have this, you are going to have KT by C noise. Adding one transistor is KT by C flicker is coming because of those things. You cannot stop them. So this is how you need to work. There is another solution is you can have transmission gate. If this guy is going to give you some electrons of delta Q1, this guy is going to donate the delta Q2 of holes when both the switches are actually off, but they are not off, or they will compensate each other. So this is what people are doing in the way of transmission gate, where NMOS and PMOS switches are in parallel, and the digital symbol of this one is like this. Something like this, sorry. This is input and this is output, right? But when you are doing this, what is the problem, or what you need to take care of? You need to take care of the bandwidth, because when you are multiplying with the noise, this is decided by 1 by 2 pi RC, and R is coming from here, right? Or the resistance value has to be taken care of when you are doing this. Okay. Okay. But before that, let's ask you one more thing. Design specifications for the operational amplifier which is driving a sample and hold circuit with a sampling frequency of 1 gigahertz. So you need to tell me what specifications do you need. Let's assume that the charge injection and clock feed through, or maybe noise, all together are less than 1 microvolt. That is what we want. And this is 1 volt, and this is, now tell me, like gain, UGBW, slew rate, so what will be the value of gain? How do you find out gain, by the way? Yeah, maybe input resolution, or how much gain do you need. Right now it's a voltage buffer, by the way, right? So what is going to bother you, that if there is V in here, same V, okay, I'm drawing sample, so sampled is basically symboled with star. V in star is equal to sampled input. So I want V in star here. How much I can tolerate? 1 microvolt. So how much gain do you need? Sorry, following Raman. If you are understanding, I'm looking for answer. Vivek, what will be the answer? 120 dB. Right? How did you get 120 dB?
1 microvolt.
Yeah, 1 by 1 microvolt. Right? Because I'm taking the slope of going from 0 to 1. Going from 0 to 1. I'm expecting this voltage change has to be happen in 1 microvolt. This is from 0 to 1. So 1 divided by 1 microvolt is going to give you 10 raised to 6 volt per volt, which is going to be 120 dB in decibel, right? Yes, Siddhant, are you following or no? Right? Okay. Because This is what we need to do every time. Whenever you are seeing op-amp, you need to find out at least 3 4 you know these specifications needs to be derived. So now tell me, what is the UGBW requirement? Look, if sampling frequency is 1 giga, we already taken care of Nyquist rate. Maybe the input is at least twice of smaller than what we have, right? So input might be 500 uh, 0.5 gigahertz, right? Or maybe lesser than that. It cannot be more than that. So UGBW is at the higher end. So at least 10 times what you are requiring. We are making some budget. What will the slew rate in that case? dV by dt. So if your clock is 1 giga, you need to make sure that this slewing has to be with some budget. You can make some budget and you can find out dV max by dt. So dV is already known to us, which is 1 volt divided by dt. Let's make budget of 0.1 nano. So 10 volt per nanosecond will be helpful. I'm making some budget. This might be some different number for your case. You can make even more tight budget and you are saying 0.01 nano. It will be difficult, but you can make some budget if you want, right? As you are increasing this, actually your current requirement is also increasing, right? Because dVo max by dt is nothing but C by I. Sorry, I by C, right? So as you need this one more and more steeper, the current will be increasing for a given capacitor. Capacitor is the node capacitor at the output, right? So any problem till now or no? Then maybe we can talk about other things next time, and then we'll go to the GMC filter or switch cap filter. Have you studied by chance anywhere filters? Have you studied filter ever, Siddhant?
This filter
Any filter?
normal filter for
Okay. What have you studied in filter?
low pass filter, high pass filter. Option.
No, those filters I'm talking about. But those filters, what you are talking about, like this, if you have studied this one, I'm not talking about this one. I'm talking about something else, little bit higher than that. When there is active filters, have you studied active filters using op-amp? But when we are talking about passive plus active plus something, so have you studied the approximations also? This is what I'm asking. Those are Butterworth, Chebyshev, Bessel, elliptic, many are there. Okay. Don't worry, if you this is not part of our course, but yeah, if you know this, so these are defining by only one thing. Yes, I wanted to tell you that low pass filter look like this one, right? In linear scale. So linear scale, actually it will not be like this, but in reality this is defined as passband ripple, and this is known as stop band ripple, and this is called roll off.
So this is for all the this is for all the filters or only Chebyshev?
This is for, so I'm telling you that uh, if you are designing any filter with following approximations where your major concern is either of these three, like passband ripple, stopband ripple, or roll off, then you have to choose the approximation uh, accordingly. Like if you are so much caring about this, Butterworth, like these ripples, then you should choose Butterworth. If you are so much caring about that, roll off, then you should care about Chebyshev. So these are the mathematical approximation through which the location of poles and zeros are coming on different places. They are not like, it looks here very simple, that 1 by root LC, right? But when you are adding this approximation in active filter, if it is first order, no problem. If it is more order, like fourth or fifth order, or maybe even second order, you are going to see such thing. Like I think Raman can answer this one at least. So when are you going to observe such thing? If this is minus 40 dB per decade, yeah, Raman, do you remember or no? Yeah, Himanshu, do you remember? Yeah. So if this is a second order and the roots or the poles are complex and conjugate, which is going to decide value of zeta and omega n, right? So if you are designing zeta and omega n correctly, no problem, still you can achieve this one. That response is known as critical damped, right? This is underdamped, by the way. You can make even sluggish response also. All these things are happening because of only one reason, which is choosing the value of L and C, right? So that's how you are designing three different response for second order. Similarly, Butterworth, Chebyshev, this Basel, all have given their own equation through which you are going to have the poles and zeros location, which are going to either reduce this one, or maybe roll off some people, because how it's going to start, it also depends on that, right? Sometimes here also, sometimes like this also. So those approximations are Butterworth, Chebyshev, Basel, and elliptic. Right? Generally, Butterworth and Chebyshev are the famous one which people are using. Right? So this is not only applicable to analog filters, but this is also extended to digital filters, or all the filters which has and zeros and poles are known as IR filters. Those who have only zeros are known as FIR filters. So these approximations are also applicable to there also, right? So this is what like you should know only this that much. I am not asking you to know the equations of this Butterworth, Chebyshev, Basel, elliptic. If you want to do some research, believe me, I just remember Butterworth and Chebyshev. Right? So I remember those things which I want to use it. So if you are doing some research, then you can go into all these details and you can remember the approximations also. But these are just approximations, just to make sure that how you want your response. Otherwise, the fundamentals of filters are same. And this is happening when you want to go for higher and higher order, like fifth order, sixth order, eighth order, 10th order. So that is what I wanted to know from you people. Now you know. Right? So this was just an introduction to filters. If you are more interested, I'll tell you when I'm going to teach filters in EE203. So this will be like I'm going to start from even from zero. They have never studied filters. It will be but at the end of this semester, because that's the last topic for them. So to know the approximations, I'm going to teach these two approximations to them. These are the popular one. Other one can be derived, and other than these four, there are more also available. If you like, you can create one Siddhant approximations also. So I'll be happy if you can do it. Right? Okay.